Okay, hello. Hey, I'm going to go through section 5.2, day 1 with you, and this is the integrals of natural log. Or the integrals that give us natural log. So if I'm faced with an integral of 1 over x, or this could be written as the integral of x to the negative 1 dx, the integral of that turns out to be natural log absolute value of x plus c. If you recall, when we took the derivative of natural log x, its derivative is 1 over x. So if we want to go backwards, the integral of 1 over x turns out to be natural log x. The additional item that you see up there is the fact that we want to keep this value positive. The natural log of x only has a domain where x has to be greater than 0. So I can only perform the natural log functions on values of x that are positive. So that is the reason for the absolute value involved in our answer. What if it's a little bit more complicated and we have u where u is some function? Well, we will get 1 over u turns out to be the natural log of absolute value of u. Typically, we will probably have some u sort of substitution going on, and we'll follow that down through. Then du is equal to something dx. Depending on what that function is. There could be, some coefficients going on in front here. So we'll see that play out. Let's just do a few examples. Example A, the integral of 5 over x. Well, like any multiplier, we could pull that multiplier out front of 5 and have this be the integral of 1 over x. If I look at this, maybe we're used to working with changing that to a negative 1 power. You hopefully would recognize this as 5 natural log absolute value of x. Since it's an indefinite integral, it's a plus c. Now this 5 could come back up and become a power, and I could have the natural log of x to the 5th absolute valued plus c. That would be an alternate answer as well. Maybe you thought, well, why can't I use the power rule? And here is the reason you're going to see the power rule fails us on this. X to the negative 1 plus 1 gives me 0, and then I would divide by this new power of 0. And of course, division by 0 is not going to work out very well for us. So the power rule fails us when we have a power of negative 1, because you end up with that division by 0. It indeed is its own animal. It is a natural log integration. Okay, part B. B, there is more than just an x down below. So let's just set up a quick little u sub. Let u equal x plus 1. Then du is equal to 1 dx. When I look at this problem and I transfer it over to u's, I'd have 1 over u, and 1 dx is equivalent to a du, so I get multiplied by du. The integral of 1 over u will be natural log absolute value u plus c. Change it back to x's to format our final answer, and since u is equal to x plus 1, we're going to replace u with the x plus 1, and there's our answer. Letter C. Now this looks really complicated, doesn't it? But the first thing I notice is that my degree in the numerator is more than the degree of the numerator, trying to write and talk, is greater than the degree of the denominator. If that is the case, then we're going to want to solve this first by simplifying. We're going to simplify by using long division, or synthetic if we can. On this one, that might even be an overkill. We know these are the type we just love. So maybe it would even be easier to take x and split it up so it is its own fraction, its own denominator for each of those numerators. And now we can simplify this idea of simplifying using long division. X goes into these x times minus 5 over x dx. Well, since it's a series of terms being added or subtracted, we can indeed break this up and do 2 separate integrations. We wouldn't necessarily have to write it, but for sure it is a possibility for us. So I'm going to get from this first integral an x squared over 2 minus 5, and then the integral of 1 over x. Hopefully you recognize that. It's the new thing we're learning. It's a natural log x. And there's our answer. So anytime that numerator is greater than the denominator, we need to simplify. And in this case, since the denominator was just a single x, it's easiest to think of that heart design, and we can split it up so each numerator takes on that common denominator. All right, D. D looks tough, and D is tough for a lot of people to recognize. I could write this as 1 over x times 1 over natural log of x cubed dx. We could indeed write that. Another thing we could do is we could see this power coming back out in front, and that would give us 1 over x times 1/3 natural log x dx. Well, this 1/3 could really come all the way out front because this is all being multiplied, and I could end up with it looking like this. Now, you sub this. Let u equal natural log of x. The derivative then becomes, wait till you see this, woohoo, it is 1 over x dx, which is what we have right here. We have 1 over x dx times dx. That can be replaced using a du. So I'd have 1 over 3 times the integral of 1 over u, replace natural log x with u, and then 1x dx is equivalent to du. Well, this just turned into a nice problem, didn't it? I'm going to get 1/3. The integral of 1 over u will be natural log absolute value of u plus c. That's 1/3 natural log. Change yourself back to x's. But wait a minute. U was equivalent to natural log. Interesting. So this turns out to be a 1/3 natural log of the natural log x plus c. That is correct. Those are always hard. Trying to see this as a 1 over x, which is the derivative of natural log x, the u sub works out perfectly. Number 3, it says find the area with the log rule. And we're given y equals 2x over x squared plus 1. And it says use the log rule. So, find the area. Well, in order to find area of a curve that is not so geometrically defined as like a triangle or a square, perhaps we'd want to use calculus to do that. So we know we can find the area of this curve from 0 to 3 of 2x x squared plus 1 dx. That'll give us the, because we had this vertical line at x equals 3, I should have written that down. So what we're looking for is this region here. So under the curve between the x-axis, the line x equals 3, and our curve 2x over x squared plus 1. Well, what would that area look like? Well, if I integrate from 0 to 3, I'm going to get the area of that. So let's u sub that. Let u equal the bottom. You know how we often look to the bottom to set up our u and see if it's fruitful on this one. I would get du equals 2x dx, and indeed we have 2x dx, so that can be replaced with du. So let's revise. We'll have the integral of 1 over u, I'm taking care of the x squared plus 1, times the 2x dx ends up being a du. Let's update our bounds, and to do that, when 0 goes in, when x is 0, u is 0 plus 1 or 1. Found our lower bound. When x is 3, the upper bound, we will get u is equal to 3 squared plus 1, which is 10. So now I just need to integrate. I'm going to get the integral of 1 over u as natural log absolute value of u. No plus c because we are a definite integral from 1 to 10. And now we will substitute. We'll do our fundamental theorem of calculus, and we know that's going to be f of 10 minus f of 1. And for us, that's going to be a natural log of 10 minus a natural log of 1. Don't really need these absolute value signs. Natural log of 10 minus 0. Remember how e raised to the 0 equals 1? So the answer to natural log of 1 is 0. This turns out to be the area under the curve is natural log of 10, which actually turns out to be like 2.303. If you had had your calculator, we could have actually solved it way back there using the calculator. But because we didn't, we had to go into a U sub and do it by hand. All right, part A. This is an example where we'd want to use long division before integrating. These degrees are equal, and I think there's some simplifying that we can achieve here. So we're going to go into long division, and I know it may have been a long time since you've done long division, but you have practiced polynomial division in your previous classes. So here's my setup. Our divisor is the x squared plus 1. We ask ourselves, how many times does x squared go into x squared? The answer would be 1. Then we go into that multiplying mode. We're multiplying 1 times the divisor. The divisor has 2 terms, so I should get 2 terms when I do my multiplication. Indeed, I do. Now, don't forget that this is a subtraction when you're doing long division. And we subtract this, and we're going to get x squared minus x squared is 0. X minus 1 is going to give me x minus 1. That looks like a problem, doesn't it? And indeed it is. So let's move and align things. We can make this work, can't we? There's a skip over, isn't there, in our divisor that produces 0 x's for us. All right, now let's do this. Now, hopefully this is going to make more sense to us. X squared minus x squared gives me 0. X minus 0x is going to give me that positive x. It's kind of like that's coming down. And then 1 minus 1 gives me 0. Okay, I'm back to the square 1. How many times does x squared go into x? And you would answer none, and you are correct. So we have our answer. This is a remainder for us. And we will write it as 1 plus x over x squared plus 1. The remainder over the divisor. So what we've just done is we simplified our integral to become 1 plus x over x squared plus 1 dx. And now I think we've got a problem that we can actually solve. So we can take the integral of each piece individually because we have the addition and subtraction going on. The first integral looks way easier than the second integral. I know the integral of 1 dx will simply be x plus some c. I'm going to let my c's join up after I get done with the second integral. For this integral, I think I would choose to let my u equal x squared plus 1. Then du is equal to 2x dx. And let's see, we only need an x dx, so let's get rid of the 2 by division. So divide by 2, it's like multiplying by a half. I get 1/2 du equals an x dx. So this is going to give me 1/2 the integral of 1 over u du. This was our u, so there's my 1 over u. X dx is a 1/2 du. So there's our 1/2 du. Now we just have to integrate, and we'll have the integral of 1 over u is recognizable as the natural log of u plus some c. And I'm accounting for the c that came from here as well. So I'm going to join those two c's together and just make it into a single c. I have x's and u's. That's not great, is it? So natural log absolute value of x squared plus 1 plus c. Just a side comment on this last answer. or is the absolute values necessary? It would not. This would stay positive. This is always a positive quantity since I'm squaring something and adding a positive 1 to it. So I could get rid of my absolute values and call this x squared plus 1 using parentheses. One more little adjustment we could do, we could pull this half power back, and this could look like x plus natural log of all that to the 1/2, or we could say the square root of x squared plus 1 plus c. You know, there's three very valid types of answers. We've got this answer, which is fine. We've got this answer, which is fine. And we have this answer, which is fine. I would say a little bit on this, we could get rid of those absolute values, and that is nice to do if you think of it. All right. I think there's one problem left up here on the right. Yep. So I noticed that the degree of the numerator is definitely a degree higher than the denominator. This calls for simplifying first before we integrate. So let's simplify by using synthetic division. Been a while probably. In my box, I am going to put the opposite of what I see. That will be a -1. The typical standard form is an x minus c, where c goes in the box. For us, we would have an x minus -1, thus -1's going in our box. Copy down your coefficients, watching that this descends nicely. So I have an x squared, which is a 1 coefficient. The x has a coefficient of -3 there, and a 2. So we go 2, degree 2, degree 1, degree 0, and there's our coefficients. Start the ball rolling by bringing down that 1, and then we go into multiplication mode. -1 times 1 gives me -1. Then I add, gives me -4. Now I'm back to multiplying. -1 times -4 gives me +4. And then I'm adding, and I get a remainder of 6. Okay, now we just have to remember, how do we write this out? Well, it is a reduced polynomial. I took x into x squared. It's going to reduce it down to an x minus 4 plus 6 is my remainder. 6 goes over our divisor of x plus 1. What have we just created? Well, we created a simplified version of the original statement. So I'm going to have the integral of this answer for us right there. All right. So now I just have to integrate this. So we turned this difficult looking integral into something a little more simple. We can integrate. The x will give us x squared divided by 2 minus 4x plus, I'm going to pull the 6 out front, the integral of 1 over x plus 1 dx. And you're thinking, yeah, she's just delaying doing that. You're right. But actually we can, can't we? We found the easy ones to do. This was this one was easy to do. This was easy to do. I'm saying this. This one was easy. This one was easy. This is more complicated. So I just decided to rewrite it and think of it by itself. If I had just this to do as a problem, I would set up a u sub. I'd let u equal x plus 1, the denominator. Then du is equal to a 1 dx. Nice and easy simplifying here. So this becomes 6 integral of 1 over u du, because 1 dx is equivalent to a du. Okay, now I can see that this is going to be a 6 natural log absolute value of u, and u is equivalent to an x plus 1. I add my c, I bring down these others that I had already calculated, and that becomes the integral answer. Very good. Number 5, change of variables. We've done some change of variables before, so I think I'm going to go ahead and pass. I would let my u equal 3x plus 1 on this, and we can see that du would be a 3 dx. I have a 5 dx, so this I would have rewritten as 5 integral 1 over 3x plus 1 dx, so that I could get a 1/3 du equals dx. That will transfer over to a 5 integral of 1 over u, and then A 1/3 du replaces this dx, so multiply out front by a 1/3, put in our du. Now, the only thing I haven't done was update our bounds. When x is 0, remember how to do this? When x is 0, u is, I'm reading right here, u is equal to 3 times 0 plus 1. Well, that is going to be not 3, but 1. And then, okay, so there's a 1 on the bottom. And when x is the upper bound of 4, u becomes a 3 times 4 plus 1, giving us 13. And then we could go ahead and integrate. Of course, you know, I'm almost done. 5/3 natural log absolute value of u evaluated from 1 to 13. No reason to switch out of u's because we updated those bounds. They are now in terms of u. So you can finish this problem by going f of 13 minus f of 1. I pulled the 5/3 out front. So natural log 13 minus natural log of 1. Natural log of 1 is 0. So we get 5/3 natural log of 13. This one is a little bit interesting, isn't it? It turns out to be kind of a double sub. So once again, I really don't have a clear direction on where to take this, so I'm going to let my intuition kind of take over and let u equal the bottom. So the denominator is my u. If I take the derivative, this is like a 1/2 power, so 2x to the 1/2. That's going to give me a 1/2 2x to the negative 1/2, drops it to the bottom. Derivative of the inside is a 2, and then finally I get my dx. Mainly because this was du dx, and I multiply up and over, right? Brings that dx over. 2 cancels with 2, so let's update. We have du is equal to a 1 over 2x square rooted dx. Okay, wow. This doesn't look real clean, does it? But let's hold out a little hope. 1 over, this is my u, so that can be replaced. Dx gets replaced with a mess. Let's see, we got to get dx by itself. Let's multiply both sides by square root 2x. Multiply this side by square root 2x. All right, now we're talking dx. Dx is equivalent to a square root 2x du. That's not good, is it? We got a square root of 2x over u du. Can I integrate? No, because of the x and the u intermixing. That's not good. But remember, sometimes look at double sub. So we will double sub and see what we can come up with. We know that u is equal to 1 plus square root 2x. I'm rewriting that 1/2 power into a nice square root. Solve for square root because that's what we want to change out. So that's going to be a u minus 1 is equal to the square root of 2x. Now we'll come back over and switch it out. U minus 1 over u du. This is still not easy. Okay, let's simplify this. This is a heart 1. U over u minus 1 over u du. See where this is going? That's going to give me 1 minus 1 over u du. Integrate each term separately with respect to u. That's going to give me a u minus a natural log absolute value of u plus rc. And then change back from u's. And our u was 1 plus the square root of 2x minus natural log absolute value of 1 plus the square root of 2x plus c. Are the absolute values necessary? No, not really. So we could let those evaporate and just bring in parentheses. Because we know the square root has to be positive, and 1 is positive. Put them together, you get positive. All right. That was a fun problem. A little tricky. All right, that brings you to this homework, and I think you should be able to do everything up to The ones that pick up the trig functions. Maybe there are no trig functions. If that's the case, do the whole thing. Let me just scroll down. Yeah, you can do this whole worksheet. Go 1 through 10. Have fun.